Hey everyone, and welcome to This Explainer. Today, we're popping the hood on our planet to examine its incredibly complex climate systems. We're going to skip the noise and look strictly at the hard scientific data to understand the precise physical mechanics of global climate change. So if you've ever found yourself wondering exactly how the Earth regulates its temperature, well, you're definitely in the right place.
To do that, we have a pretty packed roadmap today. We'll start with the interacting Earth climate systems, then look at Earth's energy budget balance. From there, we'll compare biological versus geological carbon, explore proxies of past climates, examine the evidence of anthropogenic change, and finally, wrap up with climate mitigation and solutions.
Because all of this leads us to one massive overarching question. What actually happens when a planet's incredible 4.5 billion-year-old thermostat is suddenly overwritten by a massive influx of stored carbon? To answer that objectively, we just need to look at the systemic data and the irrefutable mechanics of heat transfer.
Let's kick things off with Section 1, interacting Earth climate systems, or what we can call the baseline interconnection. You see, Earth isn't just a dead rock floating in space, right? It's a highly dynamic, interconnected machine. In Earth system science, we study 5 main interacting components: the geosphere, the atmosphere, the hydrosphere, the cryosphere, and the biosphere. And the absolutely crucial takeaway here is that a shift in one system immediately cascades into all the others. You literally can't alter one piece without the whole system responding. A change in atmospheric gases instantly impacts the cryosphere's ice sheets and the biosphere's living organisms. It's exactly why a shift in distant ocean currents can ultimately dictate what crops grow in your local farming communities.
Now, this interconnectedness means we have to be super clear on our terms. Namely, weather and climate are not the same thing. Weather is the short-term stuff. It's what's happening outside your window today or this week. Climate, on the other hand, is the long-term average of those patterns. You simply can't point to a single freakishly cold winter to understand global trends. We have to look at the macroscopic data, which climate scientists measure using a strict 30-year baseline just to ensure absolute accuracy.
Moving right along to Section 2, Earth's energy budget balance. Let's track the electromagnetic flow. So how does the greenhouse effect actually work? Well, it starts with incoming solar radiation, mostly short-wavelength UV and visible light, which passes right through our atmosphere like it's invisible. The Earth's surface absorbs that energy and warms up. But here is the real secret. The Earth doesn't radiate visible light back out into space. It converts it and radiates it outward as long-wavelength thermal infrared energy, basically heat. The key here is that wavelength shift. While the incoming solar energy easily passes through, that outgoing converted thermal IR gets snagged by the molecular structure of greenhouse gases in our atmosphere, things like CO2, water vapor, and methane. They act like a giant invisible canopy, trapping the heat and keeping our planet habitable. But, of course, if you add more of those gases, you trap more heat.
Which brings us to Section 3, biological versus geological carbon, or what I like to think of as Earth's 2 thermostats.
To understand how those greenhouse gases are normally regulated, check out the stark contrast in the rates of change here. The biological carbon cycle is fast. It breathes carbon almost daily. Plants pull in CO2 for photosynthesis and release it when they decay. We're talking years to decades. The geological cycle, though, it is incredibly slow. The coal and petroleum we burn today took hundreds of millions of years of immense pressure to form, locking carbon deep underground through silicate weathering and tectonic subduction. For most of Earth's history, volcanic activity released carbon at roughly the same slow rate the geological cycle stored it, which kept the climate perfectly balanced.
But when that slow geological balance is disrupted, we get positive feedback mechanisms. And don't let the word positive fool you. In this context, it means a snowball effect, where the output rapidly amplifies the original cause. For example, as the planet warms, highly reflective sea ice melts. That exposes dark ocean water beneath, which absorbs way more solar energy, meaning a lower albedo, and that causes even more warming. Another massive one is melting permafrost, releasing ancient trapped organic matter, which decays into CO2 and methane, exponentially accelerating the heating process. When the slow cycle gets overwhelmed, it triggers these systemic cascades.
Let's transition to Section 4, proxies of past climates. How do we read the deep time data?
You might be wondering, how do we actually know what the baseline was millions of years before humans even invented thermometers? Well, we read proxy indicators. Scientists pull up deep-sea sediment cores to look at oxygen isotopes in microscopic fossils called benthic foraminifera, which tell us past ocean temperatures. We drill miles down into glaciers to extract ice cores that literally contain tiny ancient air bubbles, which are actual physical samples of the atmosphere from hundreds of thousands of years ago. Add in ancient tree rings, fossilized pollen, and boron isotopes for ocean acidity, and you've got a literal geological hard drive of the Earth's past.
And when you boot up that hard drive and compile the data, a fascinating timeline emerges. About 60 million years ago, CO2 was over 2,000 parts per million, and the planet was so hot, Antarctica was virtually ice-free. But over tens of millions of years, tectonic events like the Himalayas rising increased rock weathering, pulling massive amounts of carbon out of the air. By 24 million years ago, CO2 had dropped below 500 parts per million. And here is the kicker. The science clearly shows that for the 800,000 years leading right up to the Industrial Revolution, atmospheric CO2 fluctuated, but it never once breached 300 parts per million.
Which leads us directly into Section 5, Evidence of Anthropogenic Change, the Modern Anomaly. Today, our modern diagnostic sensors are reading over 415 parts per million of CO2. Let that sink in for a second. For 800,000 years, it never went above 300. This current number represents a rapid, exponential spike that is completely anomalous to the entire ice core record. The rate of change is just staggering. In a handful of decades, we have pushed atmospheric CO2 to levels the Earth literally hasn't seen in millions of years.
Now, a skeptic might ask, okay, but how do we know this extra carbon is from human activity and not just, say, natural volcanoes? Well, we don't guess. We look at the isotopic fingerprints. Fossil fuels are made of ancient plants, and plants have a specific chemical preference for the carbon-12 isotope over carbon-13. When we measure the atmosphere right now, we see the ratio of stable carbon-13 to carbon-12 shifting in a way that perfectly, impartially matches the signature of burned fossil fuels. It's the ultimate smoking gun, proving we are instantaneously releasing energy and carbon that took the geological cycle millions of years to lock away.
And honestly, it could be so much worse. Since 1750, humans have added over 2,000 gigatons of CO2 into the system, but only about 40% of our emissions are actually staying in the air to drive up the famous Keeling curve. A massive 60% is being absorbed by the land's vegetation and the oceans. Our planet is essentially working overtime to buffer the system.
But that buffering comes at a really steep price, triggering a whole host of system-wide symptoms. We're currently seeing an average global surface temperature anomaly of about 1.25 degrees Celsius above the historical baseline. Satellites are recording massive losses of ice mass from Antarctica and Greenland every single year. Plus, all that CO2 dissolving into the ocean is creating carbonic acid, raising acidity levels and threatening the base of marine ecosystems. And of course, as the ice melts and the ocean water physically expands from the trapped heat, we're tracking a distinct eustatic sea level rise that directly threatens coastal cities worldwide.
Okay, let's move to our final section, Section 6, Climate Mitigation and Solutions, Recalibrating the System.
Knowing the mechanics of the disruption is powerful because the scientific data actually points toward really clear, actionable mitigation strategies. First and foremost, we need to leave fossil fuels down in the slow geological cycle where they belong, transitioning our power grids to alternative, non-combustion sources like solar and wind. Second, we can use technologies like carbon capture and storage to pull emissions right at the source, coupled with widespread energy conservation. And crucially, we need international agreements like the Paris Accord to manage our forest and soil ecosystems so they can naturally draw down and store that excess carbon.
Which leaves us with one final, vital question to ponder. As our planetary heat engine continues to absorb unprecedented levels of fossil carbon, what steps will we take to restore the energy balance before our ecosystems are permanently altered? Armed with this incredibly precise understanding of Earth's interconnected systems, we have the data and we absolutely have the solutions. The real question is, how quickly can we act? Thanks for joining me for this explainer, and keep exploring the amazing mechanics of our blue planet.